Let's look next at practice test A, the second question with Hess's law. Our target equation has us looking at P4O6 as a solid plus 2 units of oxygen O2 forming P4O10 in a solid phase. This is what we would label as our target equation. We have two elementary reactions to build our target. Elementary reaction 1 has P4 as a solid plus 3 units of O2 as a gas, forming P4O6 solid. And that second elementary reaction, P4 solid plus 5 O2s yields P4O10 solid. For no other reason than it's written first, in my target equation, I generally start looking to find my first reactant. Where might I look to find the first reactant, P4O6? And again, just start skimming through the elementary reactions until you locate it. Here I have it at the first equation at the end, listed as a product. What I like about it is that it has the correct number of units. There is a 1, which matches the target value. We need a 1. But what I don't like about it is the side of the arrow it's on. In my target, it appears as a reactant, but in the elementary reactions, it's appearing as a product. Thinking out loud of a strategy, I think I need to flip the direction of the first reaction. I notice the second reactant is oxygen, O2. I'd like to end up with 2 units of O2. But the O2 appears in both elementary reactions. It's not in one unique place. The O2 is not something I would choose to make a decision on what to do with these elementary reactions. Let's instead focus on the product P4O10. P4O10 appears as a product in the second equation. Again, I'm going to ignore the O2 because it's not in a unique place. The P4O10 is unique. It's uniquely placed as a product in the second elementary reaction. Here's what I like about that. I have the correct number of units. In my target, I need to produce 1 unit of P4O10, and the target equation has just 1, so does the elementary reaction. And it's on the correct set of the arrow. That tells me I should leave this alone. So far, I've just been sharing a strategy. Let's indeed prove to ourselves that by flipping the first, leaving the second one alone, we have indeed built our target equation. Let's rewrite elementary reaction 1, but flip its direction. The original product, P4O6, now becomes the reactant. And the original reactants now are on the product side. P4O6 points at P4 plus 3O2. The delta H for this equation, simply flipping the sign, it now reports a positive 1640.1 kJs. We decided to leave the second elementary reaction just as it appears. I'll simply rewrite P4 plus 5 O2s make P4O10. The delta H remains the same value, negative 2940.1 kJs. If we indeed add these together, simplify what we can. I notice that P4s are on opposite sides of the arrow, a product in equation 1, a reactant in equation 2. They will cancel one another. I also notice that on the right side of our first equation, I have 3 oxygens, and on the left side of the equation in the second, I have 5. If I simplify, I can get rid of the 3 O2s, leaving me a remainder of 2. 5 minus 3 simplifies to 2 units of O2. And indeed we have built P4O6 left over from that first equation, and 2 units of O2, the remainder of our second equation, forming the desired product of P4O10. When I add together elementary reaction 1, its heat, with the elementary reaction 2 of its heat, we'll find our final answer. So let's hit positive 1640.1 plus a negative 2940.1. I get a value of negative 1300 kilojoules, an exothermic value.